Welcome my friends. I, Abhinav Sir, welcome you all on India's largest live e-learning platform, that is Gradeup. Okay, as all of you know that I am discussing some topics of SOM, and in the previous session we have discussed strain, and earlier also we have discussed about stress also, and in previous session I have discussed about strain and properties of material and the remaining properties of material. In fact, the major portion of properties of material I am dealing today. Okay. So my friends, this is my brief introduction. I have secured All India rank 164 in GATE 2012, and I have done my M.Tech in Geotechnical Engineering from IIT Delhi. Okay. So I have mentored more than 20,000 students, and approximately I have an experience of 8,000 hours, and approximately 25 or more cities I have teach around in this country. So this is my profile. Okay, now my friends, yes, Budev, good evening. You can see me on YouTube and app. Many of you are watching this lesson in YouTube, and many of you are watching in app also, on Gradeup app also. Okay, so my friends, today we are dealing with properties of material. My friends, so first of all, let me discuss about the failure pattern. First of all, let me discuss about the failure pattern, that how a material fails, at which angle, if we apply normal stress or shear stress. That I am going to cover first, that what will be the failure pattern, at what angle material fails by applying a force, tensile force or a torque or a torque. We will see the failure pattern on different types of material, that is brittle and ductile. Yes, many of you have joined. Good evening, Rajesh. Good evening, Khushbu. Okay, see. So brittle material, my friends, brittle material generally fails in normal stress, and my friends, ductile material generally fails in shear stress. I am again saying, brittle material generally fails in normal stress, and ductile material generally fails in shear stress. Okay, so going further, let us first of all discuss the failure pattern of brittle material. The failure pattern of brittle material. So brittle material generally fails in normal stress, that we have discussed, and ductile material generally fails in shear stress. Actually, the normal strength of brittle material is less, so generally brittle material fails in normal stress, and the shear strength of ductile material is less, so ductile material generally fails in shear stress. Okay, so first of all I am dealing with the failure pattern of brittle material. Okay, now my friends, this is a brittle material, and first of all I am taking a tensile load P acting on this brittle material. Now I want to know that what is the failure pattern of this brittle material. What is the failure pattern of this brittle material after applying P force? Okay, see, brittle material, as we all know, generally fails in normal stress, that we denoted with sigma. Okay, now before discussing the failure pattern of brittle material, first of all let me tell you something. Suppose, my friends, this is a bar and a P force is applied on this bar. Suppose this is a body or a bar, whatever you want to say it, and a P force is applied on this body. Now I want to know that what are the stresses acting on this body. First of all, since this P force is acting downward, therefore the resistance P is acting upward, therefore this body is in equilibrium. Now I want to find out that what are the stresses in this body if it will be a normal stress in this body or shear stress. See, most of you will say that the stresses here will be normal stress because you all are seeing that the force is normal to this area. But my friends, see, if you cut a body like this, then let me show you one body, let me show you two body. Then in this one body, P force is acting here, and in this body too, P force is acting upward. Therefore, we all deal it with many times. In my previous session, you all know that since whole body is in equilibrium, therefore small part must be in equilibrium. Therefore, you all know that P force will be acting upward. Now this body is in equilibrium. Similarly, this whole body is in equilibrium. Therefore, the small part must be in equilibrium. Therefore, to make it in equilibrium, P force will be acting downward. This you have seen many times in my previous sessions also. So, stress is this internal force by area, and we know the property of internal force. They are equal in magnitude. This is P, this is P, this is P, this is P, and opposite in direction. So, internal forces are, I have shown by blue color. What are internal forces? That we have seen after cutting the section. They are equal in magnitude and opposite in direction. Now, stress due to this piece, this is on normal to this area. This is P force is normal to this area. Therefore, there will be normal stress P by A. So, most of you are thinking that this will be a normal stress. But my friends, see, if I have not cut a section like this, but I am again drawing this body, my friends. Suppose my friends, this is a floor and this is a body, and P force is acting this, reaction will be P. Suppose I cut a section like this. So, this is one part, this is two part. Now, if my friends, I draw the free body diagram of one part, or if I draw the free body diagram of two part, then this P is reaction due to this and this P is force like this, my friends. Then since whole body is in equilibrium, therefore small part must be in equilibrium. Therefore, P will be acting like this, and since P is acting upward, this whole body is in equilibrium. Therefore, small part must be in equilibrium. Therefore, P will be acting like this. Now, if let me first concentrate on the first body. Let me first concentrate on the first body. Now, my friends, this P has two components on this inclined plane. One component is like this, suppose P1, and one component is like this, P2. So, my friends, on this plane, this P1 will be causing normal stress, and this P2 is shear to this plane. This P2 is shear to this plane. Therefore, this P2 will be causing shear stress on this plane. This P1 is normal to this red plane. Therefore, this P1 will be causing normal stress, and this P2 is shearing. It is tangential to the red plane. Therefore, it is causing shear stress. Now, my friends, see. Now, my friends, see here how many plane this body can have. This body can have infinite plane. One plane may be like this, 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 one plane may be like this. There are infinite plane on this body. Therefore, on those infinite plane, there will be infinite normal stress and infinite shear stress on these infinite planes. So, there are infinite planes on this body. Therefore, there will be infinite shear stress and infinite normal stress on these planes. On different planes, we are having different stresses. On different planes, my friends, we are having different stresses. I am again drawing, my friends. This was a body and this was P force on this. The reaction definitely will be P. Now, there will be, my friends, infinite. One plane might be like this, one plane might be like this, one plane may be at any other angle, one plane may be like this, horizontal also. Therefore, there are infinite planes, and on those infinite planes, there will be infinite normal stress and infinite shear stress. Okay. Now, my friends, let me first just give you a brief introduction of Mohr circle. Just let me give you a brief introduction of Mohr circle. We are not dealing with Mohr circle here, but I will show you the patterns of brittle material when this will be normal stress, and when the failure pattern of brittle material when there will be a torsion, and failure pattern of ductile material when there will be a torsion, and failure pattern of ductile material when there is normal stress. Now, my friends, those diagrams, first brittle material normal stress, then brittle material torque, what will be failure pattern? Two things. Similarly, ductile materials, when there will be torque and when there will be normal stress, there will be two failure patterns. I can easily draw them. Then you have to remember these datas and these figures. But I want that you must not remember it, but you may visualize it, or you may get the concept. For that concept, or for if we don't want to learn for that concept, we must have a slight knowledge of Mohr circle. Let me again tell you, this will be a brief introduction of Mohr circle, not the complete Mohr circle. Now, what is Mohr circle? See, my friends, let me draw two axes. One is x-axis and another is y-axis. One is x-axis, another is y-axis. So, x-axis I denote with sigma, and y-axis I denote with tau. Sigma means, x-axis means normal stress, and y-axis means tau. Tau means shear stress. Okay. So, the Mohr circle will be something like this. My friends, I am again saying, I am just giving a brief introduction of Mohr circle. So, Mohr circle, when we will go on that chapter of Mohr circle, I will give you the complete derivation, but just here I am giving a brief introduction. Mohr circle is actually a circle when we go in derivation in which center will be on sigma axis, not on tau axis. Center will be on sigma axis, not on tau axis. Suppose center is here. Center is here right now. It may be anywhere on x-axis. So, now my friends, if I cut this plane and I name this as one part, then if I draw this one part, then in this one part, this will be a P force. Since whole body is in equilibrium, therefore, my friends, small part must be in equilibrium. Therefore, P force must acting here. So, this will be a normal stress. My friends, this plane will be this plane. Because in this plane there will be only P force, there will be no component of P force. P will be like this, normal stress, and there will be no any other internal force. Therefore, shear stress, there is no force in tangential direction. Therefore, shear stress will be 0. Therefore, this will be this point. This plane will be this point, my friends. Okay. Now, my friends, this plane will be this point, and in this, my friends, in this there will be normal stress. Here P is causing normal stress, and there is no shear stress. Tau is 0. So, this is y-axis is 0. Now, brittle material fails on normal stress. I have already told you here that brittle material fails in normal stress. So, where it will fail? It will fail where normal stress is maximum. It will fail where normal stress is maximum, of course. And while giving the brief introduction of Mohr circle, this is the point where normal stress is maximum. In any other points, normal stress is less. This is the point where normal stress is maximum, and this is representing by this plane. Therefore, this body fails in this plane only. the fracture surface, if I show you, the fracture surface, if I show you, my friends, then the fracture surface will be, then the fracture surface, my friends, will be something like this. Like this, because this is the plane where normal stress is maximum. Okay. Okay, good evening ABC. Good evening Atul. Pratyashu is here. Good evening Pratyashu. Now let us go further. Now what is the failure pattern when there will be torsion in brittle material? When there will be torsion in brittle material. See, suppose my friends, this is a shaft. Suppose my friend, this is a shaft and I am applying a torque here like this. I am applying a torque here like this. I am applying a torque like this. Since on this plane, my friends, on this plane, my friends, if I am applying torque, I am not putting this plane in compression. I am not pressing it inside. And this plane, I am not tensiling it. I am not elongating it. I am just applying torque. I am just applying torque. I am just applying torque. I am saying, to this plane, I am not applying normal stress. To this plane, I am not applying a tensile stress. I am just rotating it on that plane itself, not pressing it, not elongating it. So torque will always cause shear stress, because torque is only rotating that plane on that plane itself. I am not applying compressive force. While applying torque like this, I am not applying tensile force, just rotating it. So torque will only produce, my friends, shear stress. Okay. Now, then, hello Aman, hello Gaurav. Okay. Now, if I draw a Mohr circle for torsion like this, then Mohr circle for this is like this. Okay. See why the center shifts that we will deal in Mohr circle. Just remember this, that Mohr circle for this is like this. Now my friends, brittle material fails in normal stress. Brittle material fails in normal stress. So if I apply a torque, it will causing shear stress, no normal stress. So this point will be representing by this plane. So this point will be representing by this plane, because in this plane there will be only shear. I have shown you from bottle. Okay. Now this plane will be causing only shear stress, so normal stress will be 0. Now brittle material fails in normal stress. And where it will fail, my friends? Where it will fail, my friends? Of course, if brittle material fails in normal stress, then it will fail where normal stress is maximum. And normal stress is maximum at this point. Of course, we know that. And in Mohr circle, it is at 90 degree. So in real life, in real practice, it will be at 45 degree. See that we will do in Mohr circle, that if any 2 points are suppose at theta angle away in Mohr circle, then in actual practice they will be at theta by 2. Suppose in Mohr circle 2 points are at 60 degree. Then in real life, in real practice, those 2 points, those 2 planes are at 30 degree only. Therefore, since this blue plane is only having shear stress, this will be this point, and normal stress is maximum normal stress, because brittle material fails in maximum normal stress. So it is at 90 degree. So in real practice, it will be at 45 degree. So my failure will be something like this, and this angle is 45 degree. So my failure for this is like this, and this is called as helicoidal failure at 45 degree. My friends, I can just show you the failure pattern, but from Mohr circle, I know we have not discussed Mohr circle, but from brief introduction we can learn them easily. Therefore, I have discussed Mohr circle. Okay, many of you have joined. Hello Ashish, hello Vishnu. Okay, I hope all of you are fine. Let us go further. Now ductile material. My friends, I already told you that ductile material fails in shear stress. Ductile material fails in shear stress. And suppose, my friends, there is a T torque there is a T torque applying on this ductile material. There is a T torque applied on this ductile material. Now my friends, due to this torsion, I have already discussed that Mohr circle will be, for torsion will be like this, Y center will be here, that we will deal in that chapter. Now due to this torsion, I have already shown you, suppose in this body, suppose my friends in let me go to that point. Suppose in this bottle, suppose my friends in this bottle I am applying torque. I have already shown you that it will only cause shear stress, and my friends, only causing shear stress. So this plane will be this. Why? Because on this plane there will be only shear. On this plane there will be only shear, no normal stress, only shear. Okay, so zero normal stress. So this point will be representing this plane. And my friends, ductile material fails in shear stress, and in this whole circle, where is maximum shear stress? Maximum shear stress is this point. So this plane, or all these planes are identical. These planes are itself the point of maximum shear stress. Ductile metal fails in shear stress. Where it will fail? It will fail where shear stress is maximum. Of course, it is failing in shear stress. Where it will fail? It will fail where shear stress is maximum. So it will fail here. Okay, so this will be the failure pattern, like this. It will fail. Okay, so it will fail like this while applying torsion. Okay, my friends, let us go further. Hello Diptanshu. Diptanshu from Jabalpur has joined us. Welcome. Okay, Vignesh, welcome. Okay, now if I apply a tensile force on ductile material, first of all let me again remind you, my friends, that ductile material fails in shear stress. Ductile material fails in shear stress. Now the Mohr circle for this is, my friends, somewhat like this. The Mohr circle for this is like this. Okay, why origin is shifted, that while we will discussing Mohr circle we will go in detail there. Okay. Now my friends, since in this plane I have already discussed that there will be normal stress only. See, when in brittle material, in this plane there will be normal stress only. Now in this plane there will be normal stress only, so no shear stress. That let me show you again here. This is one plane, this is P force. Since this whole body is in equilibrium, therefore it is also in equilibrium. So in this plane, so my friends in this plane, only normal stress is there. There is no shear stress. So this plane will be represented by this point. It will be only normal stress, no shear stress. Okay, and ductile materials fails in shear stress. So this plane will be representing by this point, and where there is maximum shear stress, this is the point where there is maximum shear stress. And in Mohr circle they are at what angle? They are at 90 degree. So in real life what will be the angle? Angle will be 45. So the failure will be, since ductile material fails in shear stress, and the shear stress, and my friends, the shear stress is maximum at 90 degree. So in actual it will be a 45 degree. So the failure that I have already told you was cup cone failure, when I was showing you the stress strain curve for mild steel. Mild steel is also ductile. So that angle, these angles will be at 45 degree. Okay, now we can say that how the failure pattern is we are getting, that is discussed. Okay, Archana is saying hello. Hello Archana. Mohammed is saying I can't access class from schedule. What is the problem? Okay, Mohammed, as per my knowledge, all my classes are starting at exact time, and most of other classes are also starting at exact time. Please, you can see the details of timing earlier, or the faculty always at the end of the lecture tells the next schedule. Okay, Rashid is, hi Rashid, hi Bansal, hi Vignesh. Okay, now Hi Raju. Okay, hi Shruti. Okay, hi Ashish. Now let us go further. So I am discussing now properties of material, my friends. Now I am discussing properties of material. First is elasticity. What is elasticity? If I apply a stress, I apply a tensile stress on a body and it regains after removing the load. If I apply a P force, if I apply a P force, if I apply a P force, and when I remove the loading, if it comes in original position, that property is called elasticity. And elastic limit is that point, my friends, elastic limit is that point if we apply loading, if we apply loading, if we apply loading, and if before E or at E, if before E or at E I stop applying loading, then material again comes to its original position, that is here, that is zero strain, and zero strain means no elongation or no deformation. So this is called elastic point. Elastic point is if before E or at E I stop applying load, then material again comes in original position. This is linear elastic, or material can be linear elastic or non-linear elastic also. So stress strain curve be linear also or non-linear also, that we have discussed in our previous session, that aluminum and copper shows non-elastic curve, non-linear curve. Okay, now again going forward, if it is non-linear, suppose copper and aluminum, if we load it and if apply loading, if we remove loading, then material again comes in original position. What is the meaning? I am again telling. See my friends, if this is a bar and I apply a P force on this, then there will be elongation in this bar, then there will be elongation in this bar here and here. If I remove this load P, if I remove this load P and it again came in original position, that property is elasticity. But that is only possible if I apply load beyond this E point. If we apply load before this E point, material can be linear elastic or non-linear, that depends on that material. Okay. Now going forward, if I applied load beyond elastic limit, then what will happen? If before elastic limit I have removed load, then material comes in original position. But what if I apply load beyond elastic limit? Then what will happen? See my friends, listen it carefully. We will be having numerical at the end of session on this. Please be careful. If I apply, my friends, loading like this, like this, like this, like this. If before E I remove load, material again comes here. That is zero strain. That is no change in length. But if I apply load beyond that, if I applied load, suppose this is strain axis. If I apply load beyond that, then what will happen? If I remove loading here, this is loading curve. My friends, this is loading curve. If I apply load beyond E, then unload, then the material comes like this on unloading. Then material comes like this on unloading. And what will be the angle? If the initial angle here is theta, then at theta angle material comes back, and this is unloading curve. This is unloading curve. What does this signify? This is unloading curve. This signifies that if after removing the complete load, here it is zero stress, here it is zero stress, since it is a permanent deformation, permanent set or permanent deformation, this point shows that even without application of any load, when we unload from this point, then material comes here after removing complete load, that is zero stress, but still it is strain. So in that kind of material, if I apply force P and I apply P such that that it goes beyond elastic limit, then even after when I remove this P load, then even after removing this P load, the length of the material is increased even after reduction. That is called permanent deformation, and that is unloading curve. Now again If I apply load, now again, if I apply load, then material will go like this, linear up to this point, C point, from where we remove the load. This is called reloading curve. This is called reloading curve. And this will be proportional up to here. Okay. Now, this will be proportional up to here. Proportional limit increases and ductility decreases. Ductility decreases why? That while discussing ductility, I will tell you. Okay. Now, actually Aman is asking a question that if we have to do spring for civil or not. So, actually, if you see the GATE syllabus on their official website of IIT Delhi, then spring is not mentioned in GATE syllabus. But in many questions, they attach spring to the beam. So you must have the basic knowledge about stiffness and deflection for spring. So you must have a basic knowledge. Don't go in deep, that is leaf laminated spring or closed coil spring, but you must know the deflection and the stiffness of spring. In official websites, in syllabus, spring is not written, but they attach spring to certain problems, so you must have basic knowledge about deflection and stiffness. Okay, many of you have joined. Next property, plasticity. Now what is plasticity? So, mild steel graph I have shown you earlier in my previous session. So, mild steel graph was like this. So, this region is plastic region. This region is plastic region. What is plastic region? Increase in strain without increase in stress. Here in this region, stress is not increasing, but it is going in deformation in strain. This region is called plastic region. Plastic means without increase in stress, material is so weak that it is further deforming without increase in stress. That region is plastic region, and that property is plasticity. Okay. Now, so Nitin, the 2020 YouTube session is also going on. You can see the videos there or here also. Topic is almost same for any competitive exam. 2020 is also going on in our channel. You can see there, Nitin. Okay. Hi, Chanchal. Now, what is creep? My friends, suppose this is a bar and I applied a P load on this bar. Suppose this is a bar and I applied P load on this bar, then there will be a deformation, because of course so much deformable physics. What is deformable physics? We have seen earlier. So therefore there will be deflection. There will be deflection due to this P load. Suppose this blue is deflection. Then if this P, suppose deflection is, suppose deflection is 2 mm. But if this load is applied for, let us say, 100 years or 200 years, then after long time there will be a further deformation. That further deformation is creep. Creep is the further deformation if load is applied for a long time, and load is applied, sustained loading is applied for a long time. That extra deformation due to long application of load is called creep. And you can relate relaxation also at it. Suppose if I apply a P load on a wire for a very long time, then after some time the internal resistance of that wire is reduced because you are applying load for a very long time. That property is called relaxation. Okay, let me show you in detail. Suppose this is a fixed support, my friends. Suppose this is a fixed support, and the distance between this fixed support is, suppose distance between this fixed support is 6 meters. Now I take a string, and the length of string is, suppose I say 5.9 meters, and I apply tensile force and I joined here. So length of the string was 5.9 meters, and I apply force and elongate it by 0.1 meter, and I fixed here like this. Now for a very long time, if it is fixed between these supports, that due to this creep, now the deformation is 5.95. The length is now elongated to, earlier it was 5.9, now it is 5.95 meter. Now if it is 5.95 meter, see, tension earlier was, why? The length at the beginning was 5.9 meter, and I elongate it by 0.1 meter, by 0.1 meter to make it 6 meter. I elongate it by 0.1 meter because earlier length was 5.9 meter. So earlier the tension arising in this string is due to elongation of 0.1 meter. But after a certain time, now length is due to this tension is 5.95 meter. After some time, the tension is due to 0.05 meter. Now what is stress earlier? Stress earlier was tension. Stress earlier was tension due to 0.1 meter upon area, and after long time stress is tension due to 0.05 meter upon area. Of course, tension due to 0.1 meter will be more. Tension due to elongation of 0.1 meter will be more, and tension due to elongation of 0.05 meter will be less. So stress is decreased. That decreased stress is called relaxation. Okay. Now next property is fatigue. What is fatigue, my friends? Suppose this is a marker, and if I apply cyclic loading like this, like this, like this, then it will fail after some time. Suppose this is a material and I apply cyclic loading like this, like this, like this, like this, like this, then it will fail after certain time. That failure is called fatigue. Now if I draw a graph and on x-axis I repeat number of cycle for failure, and on y-axis I write sigma, then the graph will be like this, my friends. If I apply more stress on this marker, more stress, then number of cycles required for failure will be less. If I apply less stress on this marker, the number of cycles will be more. And my friends, there will be a limit beyond which infinite number of cycles will not cause failure. If on this marker I apply force like this, very small, very small, very small, like this, like this, like this, like this, very small, then infinite number of cycles will not cause failure. That limit is called endurance limit. So below endurance limit there will be no failure. Okay. Now, what is resilience and what is toughness? So, resilience is the property of material by which it absorbs energy up to elastic limit. Resilience is the property of material by which it absorbs energy up to elastic limit. Material can be stress strain, might be linear, might be like this. So, this is the elastic limit. Suppose this is the elastic limit. So I am again saying resilience is the property of material to absorb energy up to elastic limit, and it is obtained by stress strain curve. And if I find out, my friends, this area, or in non-linear curve this area, stress strain curve will be linear or non-linear, that depends on material, then this area is called as modulus of resilience. This area is called modulus of resilience. This area. And if modulus of resilience will be more, then that material is good for springing action. Because that can absorb energy up to elastic limit. This is elastic limit and this is elastic limit. And modulus of resilience is also strain energy per unit volume. In this session I am not discussing about strain energy that I can, while telling you deflection chapter, that we can see there. Okay, now what is toughness? My friends, suppose mild steel graph is like this and cast iron graph is like this. This is cast iron, and my friends, this is mild steel. This is mild steel and this is cast iron. So toughness is the property. If I apply an impact load on this body, if it is not breaking, then this body is tough. And if I apply a load on this body and it is breaking, it is fracturing, then it is less tough. So toughness means resistance for impact loading, resistance against impact loading up to fracture. So this is the point where it is failing. So if I calculate this area, or here, if I calculate, or here, my friends, if I calculate this area, then this area is called as modulus of toughness. So modulus of toughness is area under stress strain curve up to fracture, and modulus of resilience is area under stress strain curve up to elastic limit. I am again repeating, modulus of toughness is area under stress strain curve up to fracture, and modulus of resilience is area under stress strain curve up to elastic limit. My friends, I have discussed both properties in the same slide. Why? See, I want to relate these properties. See, the resilience material is good for bike shockers or car shockers. Resilient material is good for bike shockers or car shockers. When a bike or a vehicle goes in speed breaker, I don't want that shock comes to me. I want that the shockers should absorb that shock, and shockers should not elongate permanently. So the shockers after some time should not be more height than your bike. So here there should not be any permanent deformation and it should absorb energy. Therefore we have only calculated graph up to elastic limit. And toughness is the property, if I apply load, it does not break. My friends, break. Therefore we are going up to fracture in this. Okay, let us go further. Hardness. If a material is hard, then if I apply a load, then scratch will not come, then it is hard. And if I apply a loading and scratch will come, then it will not be hard. Hardness is related to scratch. Toughness is related to fracture. Therefore we are going up to fracture. And resilience is desired for springing action. It should absorb energy. Bike shockers should absorb energy, and it should not elongate permanently. They should again regain to its original shape. Therefore we are only going up to elastic limit. More modulus of resilience, that is good for springing action, good for bike shockers. Okay. Now stress strain curve, if it is elastic like this and there will be plastic region like this, then this is called elastoplastic. Elastic, and then graph is like this. See, this is plastic, and here strain is not easy. We have to increase stress. Strain is not easy. We have to increase stress. Therefore strain hardening. Strain is not easy like this plastic region. We have to apply stress. Therefore it is strain hardening. Rigid body, I have told you many times, rigid body is that body, if we apply any force in any magnitude in any direction, there should not be any elongation. So strain will be 0. Therefore graph will be like this. And fluid, if we are in this bottle, if I open it and I pour it, then there will be a huge strain in this water, in this floor. Then even without much stress, there will be strain. This is fluid. Stress is not required. If you pour water on the floor, then it will be strain, length will be increased as compared to this glass. Therefore without much increase in stress, strain will be there. Fluid graph will be like this. Now this is the different stress strain curve for different materials, and Young's modulus like this. Of course, tan theta of stress strain curve. Suppose stress strain curve of any material is like this, then this initial theta is tan theta is theta, then tan theta I have told you in previous class that tan theta is my Young's modulus, that my tan theta is Young's modulus. Okay, this is different. Remember exception, rubber is a brittle material. Actually, the exact definition of brittle is post elastic strain should be more than 5%. Post elastic strain should be more than 5%. So B for rubber, elastic limit is here, and post elastic strain is very small. Beyond elastic limit, strain should be more. That is called a ductile material. But a rubber is fracturing, failing at very long strain. But the exact definition is that material is called as ductile, which has post elastic strain should be more than 5%, and after elastic strain here strain is very less. So rubber is treated as brittle material. Okay, Sudhir is saying you are the best, so thank you, Sudhir. Now see, I want to mention one more point. See, this mild steel has more area, so modulus of toughness will be more, and cast iron has less area, so modulus of toughness is less. Therefore mild steel is more tougher because this modulus of toughness is more. This is more tougher than cast iron. Okay, now please, on this hypothetical stress strain curve, my friends, please find out the toughness. This is the P point. Actually this is the P point, origin. Q point is yield stress. R is UTS, means ultimate tensile strength, that is maximum stress, that we have denoted by sigma U. UTS is maximum stress. This is R, S. Please find the toughness. It is given as per meter cube, that is per unit volume. So in fact they are asking modulus of toughness, that is per meter cube. Please. Thank you, Rishank. Thank you, Sudhir. Naach ke dikhao was my tagline, so many of you are saying. Okay, let me do it sometime more. Actually today my health is not very good. Thanks, Vidya. Please solve this. Manish is saying my one doubt is cleared about rubber. Okay, good, Manish, keep it up. Kshitij is saying 0.85. Kshitij, it is correct. Very good, Kshitij. Okay, so toughness, it is find in per meter cube, so that is per unit volume. So actually we have to find modulus of toughness. And what is modulus of toughness? Modulus of toughness is up to fracture the area, this area is modulus of toughness. So if I break this area in this triangle, and then here in this trapezium, and again I break this area in this red trapezium, in this black triangle, my friends, and this blue trapezium and this red trapezium. So that area is modulus of toughness, that is per unit volume. It is also asked per unit volume. So what is black area, my friends? Half into base 0.2 into height. Height is how much? 100 plus. Now my friends, what is this blue trapezium? If you apply area of trapezium, then 100 plus 140 by 2, that is 120 into 0.4. Then what is red trapezium? That is average of parallel sides, that is 140 and 135 into what is distance? 0.2. So if I find out this, we have to add all those. This will be 0.110. What will be this? 120 into 0.4 will be I think 48, and this will be 135 into 0.2, this will be 217 and 27. So 10 plus 48 plus 27, so 58, 68, 85, and this is percentage. Please remember, this is percentage, this percent per 100. So this is values 0.2%, it is actually 0.2 upon 100. This is 0.4%, it is actually 0.4 upon 100. This is 0.6 upon 100. So we have to divide by 100 also. So it will be coming out to be 0.85. So actual answer is 0.85, my friends. Okay. So this is the next question. A bar of length 2 meter. Idealized stress-strain curve is like this. Slope of initial portion is 200 gigapascal and bar is elongated up to 6.5 mm and load is removed. Then final length of bar is asked. Final length of bar is asked. My friends, final length of bar is asked. See, let me do it. I first want to know the strain. It is elongated to 6.5 mm. Elongation is 0.6. So strain is delta by L. So 6.5 into 10 की power minus 3 in meter, and in delta by L. Initial length is how much? 2 meter. So it will be 3.25 into 10 की power minus 3. This will be strain. Okay. Now let us find strain here. Strain is stress by Young's modulus. So stress is 250 by Young's modulus is given as 200 gigapascal. So 250 megapascal into 10 की power 3. This is 200 into 10 की power 6. So this strain is coming to be, I think, 200 by 250. This will be 1.25 into 10 की power minus 3. So this strain is 1.25 into 10 की power minus 3, and but we have stressed it up to more, somewhere more. This is 3.25. This is 1.25 and this is 3.25. So we have stressed more. Now we have shown that, please, if you have not seen that elastic property, after this session go there. We have shown there material again came like this and initial theta will be same. So let me say that this portion is x and this portion is, of course, this is 250. So tan theta is equal to perpendicular by base. So 250 by x. And what is this tan theta? This is Young's modulus. It is how much? 200. So how much is x? If we write megapascal, gigapascal, then x is 1.25 into 10 की power minus 3. This is x. So what will be this point? This point will be let me first rub this. This point will be 3 point. Let me take marker. This point will be 3.25 into 10 की power minus 3 minus this x. This x is how much? 1.25 into 10 की power minus 3. Therefore, it will be how much? It will be, I think, 2 into 10 की power minus 3. Therefore, this will be the strain without stress. This will be 1.25 into 10 की. This will be 2 into 10 की power minus 3. So how much is strain? 0.002. So what will be the final length? 2 meter is initial and this is 0.002. This is 0.002 will be the length. So initial, so let me once again check. This is 3.25 into 10 की power minus 3 strain. This is 1.25 into 10 की power minus 3 strain. So this is 2 into 10 की power minus 3 strain. So what is this point? this point is, I think, 2 this strain is 2 into 10 की power minus 3. Please, all of you do the calculations. All of you do the calculations. This will be the strain and 0.002. Initial length is how much? Initial length is 2 meter. Initial length is 2 meter and this is 3.25. Okay. And this is 1.25 into 10 ki power 3. Okay. So this will be the answer you will getting. Total length is 2 meter and this is the elongation. Okay. Okay, most of you get this correct, 2.004. Okay. So my friends, this is the green card from which you can access many mock tests other than GATE also, GATE, IS and many other competitive exam. From one single green card you can access any number of mock tests for any exam for unlimited number of times. Okay. Now if you like this video, please like it, comment it, share it. You can also follow me on Gradeup app. Just write Abhinav Negi and follow me. So tomorrow at 8:30 p.m. we are having our next class on elastic constants, and from tomorrow onwards numerical will be coming more. Okay, thank you.